Alright, if you're watching this video, it's because you missed the lecture on power and efficiency, so we'll do the 4 practice problems from the PowerPoint that should help you with your worksheet. Let's get started. A light bulb consumes 25 watts. That capital W is not working anymore. It stands for the unit watt. 25 watts. How much energy is used by the bulb after 2 hours? For this, we need the equation power equals energy divided by time. We're looking for energy, so if we multiply by time on both sides, that isolates the variable E. Time times power is equal to the energy. Now we just plug in. Remember, from the PowerPoint, a watt is equal to 1 joule per second. So if we have time in hours, the hours needs to be converted to seconds. In 2 hours, there are 3,600 seconds for every 1 hour. This is our time value. And we will multiply by 25 watts. And again, a watt is a joule per second. I'm going to plug this all into the calculator in one fell swoop. 25 times 3,600. Sorry, this is 2. Doesn't really matter the order. 2 times 3,600 times 25. In 2 hours, the bulb consumes 1.8 E5 joules of energy. Next question, practice 2. Cress has a mass of 70.2 kilograms. He climbs 55 meters high set of stairs in 9 minutes. What is his average power output? Power equals energy divided by time. In this case, the energy is the work he does. So this will be the work in climbing the stairs divided by time. Remember, a work is a change in potential energy or a change in kinetic energy over time. So that's going to be mgh, delta H actually, over T. His mass is 70.2. G is 9.81 meters per second squared. His initial height is 0. His final height is 55 meters in 9 minutes. In 9 minutes, there are 60 seconds per minute. So that's how I'll convert. Grab the calculator. Remember, alpha y equals, enter will give you a fraction. 70.2 times 9.81 times a height that he gets to is 55. That's the final minus initial, which is 0. And then 9 times 60. Remember, if you don't use the fraction, you have to put parentheses around the denominator. I'll go ahead and do that just as a reminder. And you get 70.14 or 7.0 E1 watts of power output. Next question, practice 3. A nuclear power plant is 45% efficient. If it produces 65 megawatts of power daily, how much power is required to operate it? Remember, or actually you weren't here, so the equation for efficiency, this weird looking symbol that I poorly drew, and I'm going to draw it again, is the symbol eta. It's typically used for efficiency, and I'm going to use it in this class as well. So it looks like an N with a long tail. Efficiency, this is the symbol. Eta, the Greek letter eta. Eta is equal to power out divided by the power in. I need to convert this 45% to the decimal form. So to do that, I'll take 45%, I'll divide by 100%, and that gives me 0.45. That's my eta. When you use this equation, your eta needs to be in the decimal form. Though if you report efficiency, it's okay to report it either as a decimal or as a percentage like this. So my eta is 0.45. The power that the power plant produced, this is the power out. How much power is required to operate it? That's how much power has to actually go into the plant, how much energy per second the plant has to consume, either in the form of coal, nuclear power, hydroelectric power, whatever, or with a rate of falling water with dams. Whatever the energy source or the power source of the plant is, that's how much power is required to operate the plant. So that's the power in. We're going to be solving for power in. So I will, in this equation, I will multiply both sides by power in. So I'm going to solve this for power in. If I do power in on both sides, I now have the power in on this side of the equation, the left side of the equation, and then I can divide by eta on both sides. That moves the eta away. This equation now looks like power in is equal to power out divided by eta. So now we just plug in. I'm going to leave it in megawatts. That's fine. 65 MW, that's 65 million watts divided by 0.45. Grab the calculator. 65 divided by 0.45. That equals 144 or 1.44 E2. So 1.44 E2 megawatts of power is required to operate the plant. Practice 4, last one. Destiny weighs 667 newtons. She climbs an 8-meter high ladder, generating 42.3 watts of power. How much time does it take her to climb the ladder? Power is equal to energy over time. We are looking for time. So if I multiply by time on both sides, and I divide by power on both sides, this isolates my variable t. Time is equal to energy divided by power. Destiny does work, so that's going to be her energy is going to be the work in getting up the stairs. And the work in getting up the stairs causes a change in her potential energy. So that's going to be mg delta h, change in the height, height final minus initial. Initial height is 0, so it's just going to be mgh final. Mg is 667. This is the height. 42.3, this is the power. So we can plug in mg times h over p. Mg is 667 times a height of 8. This is times 8 divided by 42.3. I grab the calculator. 667 times 8 divided by 42.3. And this is 126 or 1.26 E2 seconds. This is the SI unit. Takes her a while to get up the ladder. 8 meters is quite high. All right, I hope you found this video helpful. Thanks for watching. Email me if you have questions, and study well.